Alright guys, so this will be our last chapter, okay? This will be a really short chapter, only about actually like 3 sections, one skills check, a little bit of homework, not a whole bunch, and a test. But it's mostly about waves and all those things. So let's get started. So when we talk about waves in terms of physics, okay, which waves you've all heard of, most of the time is just like those waves in the ocean, which is a type of wave in general. But we're first going to look at what we call mechanical waves. And what a mechanical wave is a disturbance in matter that carries energy from one place to another. So it's some disturbance that allows energy to go from point A to point B. Right? And this is created when a source of energy causes a vibration to travel through a medium. Okay? And we'll describe what a medium is in a second. But it's when you have some sort of input of energy, it has a vibration that causes that energy to travel through a medium. And there are 3 types of mechanical waves we'll talk about, and one other wave that we'll mention at the end very quickly. One thing I want to mention first, though, before we move on, is when we talk about vibrations, you've all heard of vibrations, but when we talk about vibrations in the actual physics definition, that's a repeating back and forth movement. Okay, so when something is going back and forth, back and forth, back and forth, that's a vibration. That's what we'll symbolize as a vibration. Now, when we talk about the mediums, like I just said, okay, this is the material through which a wave travels. Okay, and this is required for all mechanical waves. So all the 3 types of mechanical waves we talk about have to have mediums. All right. And these always go back to normal when the wave travels through. They don't travel with energy. So the actual medium never changes, okay, in the end. It might change during the wave, but it'll always go back to normal. It won't ever change after the wave goes through it. Some examples of it are like solids, liquids, gases, water, air, the ground. Okay, those are all can be examples of mediums. But what's not an example is space. Space is not a medium because that's just space. And a vacuum chamber. All right. Those are 2 prime examples that are not mediums. Okay. Almost everything else can be medium, right? Rock, air, water, anything like that. So let's talk about the first type of mechanical wave, which is what we'll call a transverse wave. Okay. This is a wave that causes the medium to vibrate at right angles to the direction of the wave it travels. It might seem a little bit weird, but I'll show you in a second. But what's happening is, in terms of the particles, they are displaced perpendicular to the direction of the wave. Okay. So let's say a wave is going towards the right. Okay. Particles will be displaced going up and down probably. That's 90 degrees, right? 90-degree angles. So what's happening, a lot of these waves you've seen before are like jump ropes, okay? Or like a string where you have this sort of up and down motion. That's what you guys really most of the time would symbolize if you see like a wave, okay? Whereas this up, down, up, down, up, down portion, okay? And how we'll actually symbolize points of this wave, so the points of this up, down, hilly type of thing, okay? We're going to call the top, this top, the highest point of the wave that it reaches, okay, called the crest. Okay, because if you look at it, this is the starting point. So right here in the middle of this whole wave, that's where it started at. Okay, because that's where the hand placement of the person holding this thing, that's where it initially started. That straight line, that dotted line. So the highest point it reaches, that's the crest. While the lowest point it reaches right here is going to be called the trough or trough. There's a lot of different ways people pronounce it. So we have the crest, which is the highest point. The trough is the lowest point. Now again, when we keep talking about transverse waves, okay, I talk about the jump rope as an example of up and down. Some other examples are light waves, waves on water, radio waves are an example, and guitar strings. Okay. And looking at it again, the crest and the trough, okay, here is the direction the wave is going. It's going towards the right. right? It's starting at this dotted line. That's like the initial point of the wave starting, okay, where it hasn't moved. And then it's going up, down, and that top portion is the crest, okay? That bottom portion is called the trough, and then we'll call that the middle portion, the rest, or the beginning portion, whatever you kind of want to describe, but that's like the starting point, okay? Now we're going to talk about longitudinal waves. Okay? This is a wave in which the vibration now is parallel to the direction it travels. So if a wave is traveling to the right, okay, the vibration it travels is to the right also, compared to longitudinal, meaning transverse, which if you go back real quick, okay, the waves are moving at up and down portion, right? So if you see, the waves are moving up and down while the direction is going to the right. Let's talk about the perpendicular of it, okay? While compared to, again, longitudinal, the vibration is parallel to the direction. Now, these don't have crest and troughs. Instead, they have a compression area and a refraction area. The compression is the area where the particles in the medium are spaced close together, so it's like being compressed, right? The refraction now is the exact opposite. That's where they're spread apart, they're spread out. Okay? And as the compressions and refractions travel along the wave, I should forget my either, each particle vibrates back and forth around its rest position. So they'll go in a back and forth motion. A great example of what a longitudinal wave is one you've all seen, a slinky. Okay? Where you have this separation right here, this space and current, that's the refraction, right? That's where the slinky, like the metal, is very spread along. While the compression area is this compressed area. That's where the particles have been compressed together. So again, you see, this slinky is probably moving towards the right, and the vibration moves towards the right along with it. So this compression area will move the same direction as the direction of the wave, right? And if you want to test this out, go get a slinky, right? Or if you've seen a slinky before, if you push it one way, right, you'll see that compression area go all the way towards the direction you pressed it. Should be a 2 still there. I don't know why it's a 1. But comparing the two, okay, this animation, you see the transverse wave is going up and down while the direction of the wave is going towards the right. Okay, that's why I talk about the perpendicular nature of a transverse wave. While a longitudinal wave, you can see the compression area travels as it moves along to the right. So it's parallel as it goes for it. So transverse waves, they move perpendicular to the direction. Longitudinal, they move parallel with the direction. Okay. This animation gets very trippy after a while. The last type of mechanical wave is called a surface wave. Right? And these are waves that travel along a surface separating two media. And this usually occurs in a circular pattern. So you usually see it occurring in a circular type of way. Okay? These still contain crests, and troughs, but now the crest is going to be the particle as its topmost part, and the trough is going to be where the particle is at the bottommost. Okay, so same type of concept, but now we're looking at where the particle is at and not the wave. But there are going to be two motions now that are going to combine to create a circular pattern. And a great example, again, is ocean waves. Which, if you look at an ocean wave, if you have like a buoy, right, in the middle of an ocean, all of you, hopefully, maybe have seen this at one point, okay? Or a bobber if you're fishing or something like that, okay? As the wave, this arrow symbolizes the direction of the wave, okay? As the wave is moving right, it's going to move this bobber in a circular actual pattern. So it's never going to actually move with the wave, which the wave is going towards the right. It'll stay in the same spot, but it'll move up with the wave, and as it goes up, this highest point here will be the crest, and then it'll rotate back down starting at its rest position, which will be the trough actually, because that's the lowest point. But it'll always move that circular pattern going over, up and down in a circular motion, never actually moving from that initial spot. So those are the three types, and we're going to talk about one last type of wave in general, okay, which isn't a mechanical wave, but it's important we talk about earthquakes, which are seismic waves. Okay. These are the energy waves, waves of energy within the earth, okay? And the medium that's always used in seismic waves is that rock or other materials in the earth. Okay, so seismic waves always rely on the materials within the earth. Okay? And these are caused by those earthquakes. So when you have those plates rubbing against each other that cause earthquakes or volcanic eruptions, okay, that's going to cause waves of energy that will dissipate and be felt throughout other places, right? That's what an earthquake is. There's those seismic waves being felt throughout other places, right? So like the initial point of an earthquake starting is always going to be the worst because that's where the highest amount of energy, the highest amount of wave energy is. While as it goes out, it gets smaller and smaller. But that was an important one to talk about really quickly. And how they actually work, okay, they actually display all the three types of mechanical waves. Okay. They have what we call the transverse again, the first wave we talked about, okay, which is actually the secondary wave in the seismic wave, which is moving parallel with it because it goes up and down. Okay. They also have the longitudinal one, the parallel, the primary waves, which we'll talk about, which has compression within the actual rock going along with it. So like if you were to break this one down, you would see in these waves you'd have compression and refraction happening, and also surface waves, where after a certain amount of time it dissipates, where you've seen that, where the, like I just talked about, the initial point of an earthquake is the worst, while the farther and farther away you get from it, the not better it is, but the smaller that seismic wave is actually. But seismic waves display all three types of waves. Just looking at it again, okay, it contains that P wave, that transverse wave, it contains that longitudinal one, and that surface wave. So when you put it all together, okay, it actually looks like this bottom one, okay, where you have the direction it's going, where it gets smaller, you have the secondary wave, and you have the primary wave where you have some compression going on and refraction, okay, but they're all occurring at the same time. But that's really waves right now, okay. All right, so that's the first lesson. All right, if you guys have any questions, let me know. We just have 2 more to cover, and then we'll be done with this one. So.